Okay, we're back and we're doing some angular momentum. And for rotations, a lot of students find these to be some of the harder ones to get their heads wrapped around. These are collisions. We're talking about, in these two examples, we're about to do inelastic collisions where things stick together. It also combines the two different cases of angular momentum, basically the two definitions that we have, which are listed down here. I'm boxing them in. And, you know, we do this substitution game when we go from linear motion to rotational motion. And if we're used to saying that linear momentum is mass times velocity, okay, the classic definition, we make changes and say that L momentum, or angular momentum, moment of inertia replaces mass, and then we have angular velocity replacing velocity. So this definition works when you have real objects that are actually rotating, that have an angular speed. It just makes sense to use that. Now this other definition, MVR sine of some angle, that's what we use when we have point masses moving. You can literally define, even for something moving in a straight line, you can define an angular momentum relative to any point that you want. So if something's moving, it's some distance, that distance being r, away from the point that you define, and there's some angle between those two lines, the radius line and the line of motion, then you can define an angular momentum. It's that simple to do. Now, conservation of angular momentum happens when there's no net torque, no external torque acting on some system. Remember, momentum of any kind is conserved for systems, not individual objects. So, one of the cases that we have is something like this. Imagine if you're on a playground and you have one of those big spinning discs, like a little merry-go-round. You know, kids sometimes will run and jump on them, or they're on them to begin with, and it's spinning, and they jump off, and the disc spins faster. Things like this. But here's some weird case where, in this picture over here on the left-hand side, it's an overhead view. We're looking down on this big spinning disk. It has some moment of inertia. It has an initial angular speed. And what we're going to assume is that a skydiver comes out of the air and lands on top of this spinning disk and sticks to it. So we'll consider this to be an inelastic collision. So in this case, you know, clearly linear momentum is not going to be conserved because things are spinning. The direction of motion is changing for any point on the disk. So we have no choice but to use angular momentum. There's no net torque acting on the system. And so let's just kind of see what happens. What's more, we're going to jazz this up a little bit and say that the skydiver is coming in at some angle right here relative to the disk. So we have to use both versions of our definitions for angular momentum. Initially, you definitely have a spinning disk. So the inertia times that original angular velocity is the angular momentum of the disk itself. Okay, and now here comes the skydiver. Okay, and you know, what we're basically saying is that the skydiver's coming in at some angle. It's not landing, it's not falling and landing straight on, you know, onto the disk. So what we're saying then is that there's some distance away from the axis of rotation. We're calling that r. The skydiver's coming in. If we look at the side view, it makes an angle. So I'll also draw in the overhead view. We can assume it's coming in something like this. Okay, so there's there's an angle relative to that radius line that it's hitting on top of the disk. Okay, that's our angle beta right there. So if we look at this, there's two things that we need. Okay, so relative to the axis of rotation, relative to the center of the spinning merry-go-round, the skydiver has one piece of motion. Let me change colors here. Make it in black. That's perpendicular to that radius line. It also has a component of motion which is running basically parallel to that radius line. Okay, now that part that's going parallel to the radius line has nothing to do with, it's not going to speed up or slow down the spin of the disk. It's that part that's perpendicular. Okay, that's the piece that we need. So when that's falling down, skydiver has some mass. It has linear velocity, okay, but that's okay. It's landing some distance away from the axis of rotation. That's the little r that we're talking about. And then we need to find out whatever that perpendicular component is. Okay, so that's going to be, if we're defining that angle right there, that's on the overhead view, the piece that we need is the cosine of the angle. Okay, that gives us the perpendicular piece. Now, afterwards, the two inertias add together. It's just like adding masses together when they stick in a linear problem. So you have the inertia of the disk. Now the skydiver is acting like a point mass. You know, point mass's inertia is mr squared. So we've got the mass of the skydiver times the radius squared that it lands from that axis of rotation. And then you're going to have some final angular speed. Okay, so from this, we're looking at a case where you have two different objects. Both objects are moving. They both have angular momentum. Afterwards, they stick together, so we have to add the inertias together. And then what we're looking for is how fast is the system moving around, okay, rotating, after the collision happens. Okay. A pretty common type of problem. Okay, now here's a second one where again you have a mass coming in at some angle. This is meant to be on a horizontal surface, so we're looking at an overhead view again. Now this bar is nailed down right in the center. That's the axis of rotation for the bar. And it's free to rotate around that. There's no friction, okay, so no external torques are going to be acting on this. And the ball just comes flying in. Now in this case, initially, the only thing moving is the little ball or particle. Okay. So that's coming in, it has mass m1. It's hitting some distance away from the axis of rotation. In our picture, that's 1/3 of the length away from the center. Okay, and it's hitting at some angle right there. So we need the sine of the angle. Okay, in other words, we need the perpendicular piece of motion relative to the axis of rotation. So part of your motion is going into, perpendicular to the stick. Part of your motion is running parallel to the stick. That doesn't do anything to help the rotation. So we're going to make use of the sine of that angle right there to pick out that perpendicular piece. Okay, and the six are sitting still. Now afterwards, if the particle sticks to the bar, everything's going to be spinning, so we need that combined inertia. Okay, so the inertia of a stick which is rotating around its center, is 1/12 its mass, m2, times the total length of the stick squared. The particle's a little point mass. That's going to be m1 times the distance it hits from the axis of rotation, okay, 1/3 the length, squared, times whatever the final speed is. Okay, so here's a case where only one thing's moving beforehand, the particle. They stick together and then everything rotates afterwards. And so we're using generically, all this stuff in the brackets is that new moment of inertia when they're stuck together times the final angular speed, which is what we're trying to find. Okay, so both of these cases they certainly look different. They're different situations, but conceptually they're the same. They have rotations involved, so we're talking about conservation of angular momentum. We have inelastic collisions, so inertias are adding together, and we're trying to find what happens after the collision. We're trying to find that final angular speed. Okay, so this is a basic kind of setup. Okay, if there aren't any net torques, external torques acting on the system, angular momentum is conserved. And the setup, these problems, you can think of a lot of different versions and pictures to draw, but the physics will basically be the same. Okay, so I hope these two examples help out, and until next time, we'll see you later.